Hello, my name is Mehdi. I am a PhD student at the University of California, Irvine, and today I'm going to present our work in distilling low-dimensional representation with a task-relevant autoencoder via classifier enhancement or trace model. This is my contact information. If you have any questions, please feel free to send me an email. And if you have any suggestions or input, we really highly appreciate that. So higher order brain regions, such as ventral temporal cortex, they encode for high-level features in objects in the environment. But this encoding process is poorly understood. But why is that? So it's partly because we are using techniques such as fMRI that contain thousands of voxels in these brain regions. And these information also contain task irrelevant information which we don't know the source of them. And also these regions of interest, they usually encode for much lower dimensions of the feature space in objects, not thousands of voxels. So one goal in order to solve this problem is to how to find a lower dimensional feature space that can best explain the performed task in these brain regions, and can be applied to other brain systems as well. But what are some considerations to achieve this goal? Well, we do not know the functional form that this dimensionality reduction happens in the brain. So we need to use a method that is assumption free. And then other thing is that the lower dimensional representation in using this technique should have two major characteristics. One is it has to reflect the task relevant information, and we have to be able to recover the original input from these low dimensional information. So what are the previous methods? We have PCA, but it's a parametric method. It doesn't guarantee a task relevant information. We have autoencoder. It's a non-parametric technique, but it does not guarantee task relevant information. And we have CNNs and other methods that cannot really reconstruct the input features, the input using the encoded information. So that's why we developed task relevant autoencoder via classifier enhancement, which is a mouthful, so I'm going to call it trace. And trace is basically an autoencoder, regular autoencoder, except that we are attaching a classifier to the bottleneck that enforces the network to learn features in the bottleneck that are not only lower dimensional, but also task relevant. Then we are going to compare a regular autoencoder with a trace network, and we are going to change the dimensionality of these bottleneck and to see how the behavior of the networks, the two networks changes as the dimensionality of the bottleneck changes. So we have two networks, trace and autoencoder, where we have three data sets that we're trying to compare these two networks. One is MNES, which is most used and commonly used data set to benchmark new deep learning models. And then the other one is a fashion MNIST. And eventually we are using the data volt signal from ventral temporal cortex that was previously collected by other groups, where subjects lied in a MRI scanner while they were looking at these different objects, instances of dogs, cats, etc., from 40 different categories. And while they were looking at them, the volt signal of the brain was collected. So the task here is looking at different objects. So we benchmark our model, the trace and AE on these three data sets. And we use four metrics in order to compare these two networks. One is the reconstruction fidelity, which is the mean Pearson correlation of each examples versus the reconstruction. So by that, we want to see that how successful we are in basically reconstructing the input with this trace model. And the other thing is the bottleneck accuracy. So once we are done with the training the trace and AE network for different dimensions of the bottleneck, we are going to extract these features, and we are using a separate logistic classifier here to see how the classification accuracy changes as the bottleneck dimension of the bottleneck changes in these two networks. And the third thing is the reconstruction specificity, which is the mean Pearson correlation within the same class versus between the same between classes using the reconstructed input. So the way that we do that, we look at different examples of, for instance, this within the same class, let's say 0, and then we get all those examples. And then we look at the average correlations of them, and we populate the similarity matrix for the within class. We do that for all class 0 versus all other classes to populate the off diagonal of the matrix. So at the end, we have the on diagonal elements of the matrix that reflect the within class correlation and off diagonal that reflects between class correlation. So reconstruction specificity is the mean of these within class minus between class. We do the same exact thing for the bottleneck specificity, except that we are using bottleneck examples, features from bottleneck examples. This is the plot that shows the 4 metrics that I just talked about for the 2 different classes on the 3 different two different networks, trace and autoencoder, and 3 different data sets. It's a little bit crowded, so I'm going to zoom in to the first 250 dimensions. As you can see, the reconstruction fidelity doesn't change between the trace and AE network. Reconstruction specificity also doesn't change between the 2 networks, which means which means that by adding the classifier, we are not actually obscuring these ability of the trace network to reconstruct the input. But when we look at the bottleneck accuracy, we can see that it does improve significantly, especially in the lower dimension for the trace network versus a regular autoencoder. And the bottleneck specificity also improves for the trace network versus autoencoder. So the trace performs much better in encoding lower dimensional task relevant information, while it can preserve the reconstructing ability of the network untouched. So how else we can understand the trace behavior? Well, we can look at how trace clusters these different classes versus a regular autoencoder. As you can see, a trace network can basically do much better in clustering the different classes, distincting different classes in comparison to autoencoder. Another way to look at it is to really look at the reconstruction. So we have different instances of number 3 here. Then you can see that trace is doing much better job in comparison to autoencoder in all different instances. And by looking at this reconstruction, we can see that it's even though that the actual image is a little bit different, the trace is reconstructing a typical or canonical tree, which means that it is able to encode the gist of this class information in the bottleneck. So we have developed and validated an approach that is non-parametric and can recover the original data with no assumption, can encode for task relevant information, low-dimensional representation of data with no assumptions, and can find the best dimension that distinct within versus between class information, and can do these better than the available techniques such as PCA, AE, and CNN. With that, I want to thank you for listening to my presentation, and I want to thank my advisor, Dr. Megan Peters, and CFAR for funding this project. And also I want to thank Neuromesh Academy for presenting this opportunity for us to present our work. And again, this is my information. Please feel free to ask questions, and if you have any suggestions, I really highly appreciate that. Thank you so much and have a great day.